proof. Difficulty means we have not understood. The idea is to be able to paint a landscape in which the proof is obvious. We'll make this entire presentation based on this quote. Pierre Diligence made this quote. In this video, we shall be answering a fundamental question in stress-strain theory. The question is, how does stress and the strain transformation work? And we'll also see the visual proof that is more compelling and more understandable. So first let's understand transformation of strain. But before defining transformation of strain, first let's take a look at definition of strain. To show what strain is, let's consider a box in a 2D space. Now let's plot grid lines so that we can express this mathematically. This box is acted upon by a force F0 which causes change in length. This change in length is modeled by an expression which is called strain, that is increment in length by original length delta L by L. This is also called deformation. This equation is applicable when there is small strain theory, and this is what we will consider for the rest of the video. Now let's take another better and compelling way to derive the same expression, and also let's take a look at how transformation of strain works. So basically, rather than keeping the grid constant, we'll transform the grid. We'll squash and squeeze and extend the grid so that box will take that form. Next, we'll move on in this video to 3D representation of stress and strain. So strain in 3-dimensional is, let's consider a cuboid, and there are 3 strain. Let's plot the strain tensor. So the transformation matrix that we saw in the previous slide of the video is equivalent to the strain tensor. Here strain is acted in x direction, in the x direction, and that results in the deformation of the cuboid box that we see here. That is represented by a tensor which is called strain tensor, which as we can see on the screen. Since strain and stress can be directly proportional to each other in small strain theory, so there is a very similar tensor that is called the stress tensor that can be observed right now on the screen. So both these tensors are responsible for the deformations that happen in the space and the transformation of the coordinate axis. And to understand transformation of space, we will go to the linear algebra where the basics of transformation are covered. So let's take a look at what transformation is and what matrix does to the 2D space. So let's go back to 2D coordinate axis and let's make circle, rectangle and some other vectors in it so that we can model it and keep a map of it, to keep a track of it. When this coordinate axis is acted upon by transformation matrix A, it will change the dimension of the coordinate axis and thereby making it a new reference plane. So let's see what effect it happens on the coordinate axis by this visualization. Now let's take a look at the matrix A transpose. So what happens when we take a transpose of a matrix? So moving on to the transpose of a matrix, here we can see it will change, it will flip the entire grid and thereby making it the visual representation that we see here. Having seen what transformation does to our coordinate axis, let's see what a consecutive number of transformation does to a coordinate axis. So first let's let the coordinate axis undergo transformation A. Now we'll also apply another transformation on this coordinate axis B. Both this matrix will change the coordinate axis one after another. So this is what we get on applying 2 consecutive transformation on the coordinate axis. Now we'll put in the vector that is initially there, that a green vector represents the initial position of the vector and the red represents the final position of the vector form. Now let's just take a hypothetical question when there are 2 same matrices and we'll multiply these 2 matrices to see what we get the resultant answer. So on multiplying these 2 matrices, we will get a matrix that would look something like this. So now let's see what happens if we apply this matrix on the transform. So if we apply this matrix on the coordinate axis, we get the same final vector. This means that multiplication is equivalent to 2 consecutive transformations. We'll use this fact for the future video part. Understood what multiplication is. Let's take a transformation matrix T. Let's put it aside on the left upper corner. Now we'll take another reference coordinate frame, that is R, that is 3, 2, 2, 3. Now we'll see what happens when there are two coordinate frames and how to see what is the effect of transformation from another coordinate frame. So in this case, the reference coordinate frame is R. So these two vectors that we see, that is the red big vector and the green big vector, are the new reference coordinate vectors. Now let's take an inverse of this matrix. We'll see why we took the inverse of this matrix. So basically what happens is that if we go into the reference coordinate frame and if we want to come back to the original coordinate frame, what we can do is we can take the inverse vector, inverse matrix, and then come back. So if I can go at some place by forward method, then I take the inverse method to come back to where I was. So first I took the inverse R, that is inverse of the R matrix. Then I'll come back to the original reference frame where the tensor T will apply transformation, and then I'll again go back to the reference frame by multiplying with the R matrix. So writing this mathematically, what we get is R inverse TR. So having understood how to change the reference frame and how the transformation changes between reference frame, let's take a look at the fundamental question, that is, what is the strain and the stress at an angle inclined to the horizontal axis? Let the line be at angle theta, and now we'll calculate strain and the stress tensor at this line. So what we'll do here is that we'll apply the concept that we learned in the previous part. These are the two vectors, that is parallel and perpendicular to the angle theta line. We know what transformation tensors or the strain tensor, stress tensor represents. So we can use those strain tensors and then we can change the reference axis to V normal and V parallel, and thereby get a new tensor that would be applicable to that, and that would give us the strain and the stress that is parallel and perpendicular to the line. Now let's take a look at transformation equations. So basically, having understood that concept, the transformation equation would look something like this. So since the angle is theta and the rotation is being taken place of the axis, so what will happen is that we have R inverse TR. So here the T is the original tensor, R inverse and R are the rotation metrics. So in order to go to the new coordinate axis and to come back to the original coordinate axis, we'll plot them, we'll write them mathematically, and calculating it, we'll get these three equations. Now these three are the fundamental equations, and we can change the value of S11, S12, S all these S values, and thereby get the equation of stress strain transformation. So now we'll plug in the values of S11, S12 and all these values and get the fundamental equations that are used in the books. So on substituting the components of strain tensor, we get the following equations. These are the equations that we have mostly seen in the books, and now it will all start to make sense why we did all this transformation and how linear algebra played the role in deriving these equations. Similarly, we'll take the look at for those equations of the stress tensor. So basically, here we got the transformation equation of strain and the stress tensor using linear algebra by applying all the concepts and the visualizations that are used in linear algebra. Now let's understand why did we do all this rumpus, and what is the main reason for modeling this transformation in the first place. So basically, in architectures we need to build stress profiles. These stress profile will determine where the stress is what and how much more stress will it cause to reach the yielding point. So basically, since we need to find the points where the fractures can occur, so we'll use the yield criterion, and for that we need to find the different stress transformation at different angles. Otherwise, we might make mistakes in our calculations and thereby resulting in the failure in the equations. So now we'll see the stress profile in this image. So basically, as we can see here, there are different stresses at different angles and different positions. Therefore, we need to find different stresses, and for that we'll use this stress transformation equations and resulting strain transformation equations. I would like to thank the Menem library, which is made by the YouTuber 3Blue1Brown, and this video won't be possible without writing the code that could have been not written without the help of this library. I thank you for hearing me.